Okay, so now we're going to continue on with this proof by cases and prove for n is odd that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So in this case, before we showed that basically we showed that we had n over 2 cases, n over 2 things that sum to n plus 1. Here we're going to show that we have n plus 1 over 2 things that add to n. And so we have 1 plus 2 plus 3 plus 2 n minus 3 plus n minus 2 plus n minus 1 plus n. In this case, we're going to pair up this with this, this with this, and this with this, and so on, pairing up the ith with the n minus ith. And that's going to give us things that add up to n. But we have to ask ourselves, how many of these things do we have? So over here, it looks like we have n over 2, or sorry, n minus 1 over 2, because we have n minus 1 things that are being broken up into pairs. So we have then n minus 1 things that add up to n, which is the same thing as n minus 1 over 2 times n. But we also still have this n hanging out over here. So what is that? If this would be the same thing, we have to make these some common base. So that's n minus 1 over 2 times n plus 2n, or yeah, 2 over 2 times n, which if we shove that together, that's going to give us n plus 1 over 2 times n. I'm skipping a step of algebra that you guys should be able to follow, but just to spell everything out for you, we can pull the shared n out of both of those guys, and that gives us n plus 1 over 2 times n, which is just the same thing as that n plus 1 over 2. Therefore, it also holds in the case where n is odd. So what if we want to prove that n squared plus n is even for an integer n? Well, in this case, we're also going to do the odds and even cases. So we will prove the statement for n odd and n even. So if n is odd, then there exists a k in the integers such that n is equal to 2k plus 1. In that case, then n squared plus n is equal to 2k plus 1 squared plus 2k plus 1. This is equal to 4k squared plus 4k plus 1 plus 2k plus 1 is equal to 4k squared plus 6k plus 2. That is equal to 2k squared plus 3k plus 1. Because this guy is an element of the integers, it's just the sum of multiples of integers, therefore it's an integer, and it's being multiplied by 2, therefore this is even. Now, if case 2, sometimes it's nice to also mark off your cases. It makes it a little bit easier to read. In these cases, we have so few cases that it's pretty easy, but it's still a good habit to have that I should be more explicit about. Now, if n is even, then n is equal to 2k for k in the integers, some k in the integer. Therefore, n squared plus n is going to be equal to 2k squared plus 2k is equal to 4k squared plus 2k is equal to 2 times 2k squared plus k. And again, this guy right here is in the integers, times 2, therefore n squared plus n is even. Therefore, it holds for both, holds for all our cases. And squared plus n is always even. QED. I don't think I've written that at the end of any proofs yet. Some Latin. So the last two things were both, our cases broke up into odd and even. That is a very common breakup, but it's not by any means the only one that you will have to use. So for n squared, we're trying to show that if n is an integer, then n squared is greater than or equal to n. That's what we wish to show. We will break this up to 3 different cases. One, n is equal to 0. 2, n is greater than 0. And 3, n is less than 0. So if n is equal to 0, then n squared is equal to 0 is greater than or equal to 0. No big deal there. So this is case 1. Case 2, if n is greater than 0, then n squared is going to be greater than n, or greater than or equal to n, because for any positive integer, this is going to be a growing function, and basically the same thing, although even clearer for case 3. If n is less than 0, then n squared is going to be greater than 0, which is also greater than n, because n is negative. So it holds in all 3 of these cases. This isn't a very interesting one, but does the job. So x squared is non-negative for a real number. So if x is in R, then x squared is going to be greater than or equal to 0. First off, we need this to be greater than or equal to 0 because we're going to break this up into 3 different cases. And if we had, so our case 1 is going to be x is positive, i.e. x is greater than 0. Case 2, x is negative, i.e. x is less than 0. And case 3, we'll break this up into 3 cases. X is equal to 0. And that's why we get the non-negative. Both of these guys are going to be positive. So case 1, if x is positive, then x squared is going to also be positive. Case 2, if x is negative, then x squared is going to also be positive because the square of a negative number is positive. And case 3, if x is equal to 0, then x squared is equal to 0. In all of these cases, x squared is going to be greater than or equal to 0. Therefore, we have proven what we want to prove. So the triangle inequality, this is a very important inequality in math. X plus y is less than or equal to x plus the absolute y. So the absolute value of x plus y is going to be greater than or equal to the absolute value of x plus the absolute value of y. So we're going to break this up into 4 different cases. Case 1. Actually, I'm just going to draw a Punnett square of cases. Go back to your high school bio classes. So x is greater than 0, is less than 0, y is greater than 0, y is less than 0. So case 1, both x and y are, we need greater than or equal to 0 to make sure that we have every case covered. Case 2, so I'm going to do this as 1, 2, 3, 4. That order will make more sense in a minute. So if both x and y are greater than or equal to 0, then we have the absolute value of x plus y is just equal to x plus y is going to be, and then these guys, x plus the absolute value of x plus the absolute value of y is just equal to x plus y. Therefore, in this case, the absolute value of x plus y is equal to the absolute value of x plus the absolute value of y, which therefore absolute value of x plus y, so this is case 1, is less than or equal to k plus absolute value. So case 2 looks very similar. absolute value of x plus y is equal to, actually becomes negative x plus negative y, and then the absolute value of x plus the absolute value of y is equal to absolute value of, or is equal to negative x plus negative y. So then we get this guy, x plus y, is going to be, again, less than or equal, in this case, actually just straight up equal to, I'll write that step in, plus y, therefore x plus y is less than or equal to absolute value of x plus absolute value of y. Case 3, so this is the case where x is greater than or equal to 0 and y is less than 0. So in this case, we have the absolute value of x plus y. And this one we're actually going to have to break up into 2 subcases. So this one we have 0, y is less than 0. Case 1, x plus y is greater than 0 and greater than or equal to 0. And then the other, so this would be 3.1 in case 3.2. X plus y is less than 0. So in this case, if we look at x, so this is the same thing as saying the absolute value of x is greater than or equal to the absolute value of y. Same thing as saying the absolute value of y is greater than the absolute value of x. So here we have x plus y is going to either be equal to, in this case, we get x minus the absolute value of y, or, so case 3.1, as opposed to up here, which is definitely less than or equal to the absolute value of x plus the absolute value of y. That's the same thing as that. So I'm just going to write this as an extra step. So x is equal to the absolute value of x minus the absolute value of y is less than or equal to plus y. Cool. This is because the absolute value of y is going to be non-negative. So case 3.2. Two is the equivalent of saying the absolute value of x plus y is equal to the absolute value of y minus x is equal to the absolute value of y minus the absolute value of x, and that is going to be less than or equal to the absolute value of y plus the absolute value of x. Therefore, it holds in both subcases. So congratulations, you just did your first cases within cases, which happens sometimes. Case 4 is symmetric to case 3. because we can just relabel x and y. Therefore, it holds. Cases. Therefore, plus y is less than or equal to value x plus. Cool. And I'm going to stop this video.